Here in Lecture 14, we're going to take a look at stream iterators, which allow you, for example, to have the result of a copy or transform or for each algorithm go to the user's screen instead of into some container. And we're also going to take a look at function objects, which are yet another way, in addition to ordinary functions or template functions, of providing operations to algorithms such as transform and for each. So here on slide 2, we're introducing the idea of an ostream iterator. To declare an ostream iterator object, of course you have to have a name for your object, and the ostream iterator has to have a type of data that it's able to write to the output stream. For example, if you want to write ints, then the type here would be int. Or if you wanted to write doubles, the type would be double. And then in parentheses, you specify the output stream object that you want your ostream iterator associated with. Typically that's something like cout. There's a second form of constructor for the ostream iterator, which allows you to specify a delimiter character that you would like to have appear between the objects that are displayed. By default, there is no delimiter, and the output values simply come out crowded together with not even a space in between them. So here on slide 3, we have the first part of an example program using some ostream iterators, and on slide 5, we have the output produced by this program. V is our vector of int, initialized with 471349. And we're creating an ostream iterator for ints named OSI associated with the cout output stream. Hence, when I copy from v.begin up to but not including v.end into OSI, what will happen is that the ints in the vector v will appear on cout one at a time with no delimiter between them. So they come out crowded together, 471349, with not even spaces in between. Okay, so technically that works, but it's not very readable. We're going to create another ostream iterator, OSI-SP, meaning output stream for ints with a space. And here we've got a string containing a space character, and that will be our delimiter now. So we're doing another copy algorithm in red here, copying from the vector v into this ostream iterator, OSISP, and now we get something out that's more legible. 4 and then a space, 7 and then a space, up through 9. The delimiter can be quite flexible, so here in the green code on slide 4, I'm setting up OSIC as an ostream iterator for ints with a comma, that is a string containing a comma character followed by a space. And here I have OSINL, which is the same idea but has a new line as the delimiter. Now, because I don't want a comma after the final value in my vector, what I'm going to do is run my copy algorithm from v.begin up to, but not including, v.end minus 1. That is, I'm only going to display all of the values in my vector up to but not including the last value that's actually in the vector. And these are going to be delimited by commas. Now, to display the very last element in the vector, here's a nifty trick. v.end is an iterator that is just one beyond the end of the vector, but because vectors have random access iterators, I can use a subscript operator with a negative subscript to go back and obtain the element that's in the vector prior to v.end. And by assigning this into the ostream iterator, OSINL, that causes that value to be displayed, and a new line character is automatically appended to the end. Alright, so I have the first 5 values displayed, delimited by comma and space. 4, comma space, 7, comma space, and so on. And then I'm separately displaying the final value, the 9, with a new line character after it. Finally, here's an example that we've seen before involving the square root function. But this time, instead of writing the square roots of the vector elements into a deck containing doubles, I'm going to set up an ostream for doubles separated by spaces. So this is of type ostream iterator angle bracket double close angle bracket. And when I do this transform and have the output go to the ostream iterator, I get the square roots of the values in V displayed to my screen. So we've been looking at ostream iterators. There are also istream iterators that you can technically use to help you read things from CIN, but frankly, user input is fraught with all manner of problems, and it's usually better to read user input just using a getLine function and then attempting to parse what the user typed in once you've got that line of input in a string. Now remember, we've been looking at ostream iterators, but an OF stream, which is an output stream associated with a file, or an ostring stream, which is an ostream associated with a string object, are kinds of ostreams. So if you define an ostream iterator, you can use these ostream iterators with OF stream objects or ostring stream objects as well. Now, cout is a global variable. It's always available. And so, for convenience, if you find that you need to use a certain collection of ostream iterators over and over in more or less every program that you write, you can simply define a set of ostream iterators and declare them static so that you can put those things into a header. Here I've created a header called mytools.h, which sets up 5 ostream iterators that I plan to use quite a bit. An ostream iterator for ints that does not have a delimiter, an ostream iterator for ints that uses space as a delimiter, an ostream iterator for ints that uses comma as delimiter, and an ostream iterator for ints that uses newline. And then we could continue the same scheme with ostream iterators for doubles, ostream iterators for chars, etc., etc. There is one other little picky detail I want to point out on this slide. We did not use our using namespace standard statement to pull all of the standard library object and class names into the global namespace. This is why we have prefixed ostream iterator and cout with std::: everywhere in this file. Then on slide 8, continuing in the mytools.h header, I'm defining 3 type defs for function interfaces that I plan to use quite a bit with algorithms. For example, FDI is going to be a type def representing pointer to function that takes an int and returns double. FDD will represent pointer to function that takes double and returns double. And FDDD is going to be a function that takes 2 doubles as arguments and returns a double. So we have 2 unary functions here that take an int and return a double, and that take a double and return a double. And we have 1 binary function that takes 2 doubles and returns a double. On slides 9 and 10, we have a brief test program making use of the ostream iterators and the type defs from the mytools.h header. The output of this program is shown on slide 11. So let's take a look at this little program. V is a vector of int, initialized with 471349. Now, so that I don't have to type v.begin and v.end everywhere, I'm going to create vbeg as an iterator initialized with v.begin and vend as an iterator initialized with v.end. This way, in my algorithms like copy, I can use vbeg and vend to represent the range of values that I want to step through in my vector. In this blue copy algorithm, I'm going to use the OSI ostream iterator, that is the ostream iterator for ints with no delimiter,